Hi there, my name is Devashish, and this is the channel I'm starting today as a way to explore the details of science. Science, as the channel name talks about, is a boring subject in some ways. There's a lot of hard work involved, there's a lot of details, there's a lot of grunt work actually, which you have to do day in and day out, which you have to really follow down in great details to understand how nature works, how the universe works, how the world works. And my goal for this channel is to actually dive in great details about different topics of science, especially physics. I'm a physicist, and that's why I've studied basically physics for more than a decade. I did my PhD in experimental physics, and right now I work in industries building some of the biggest microscopes on the planet. And what I really wanted to do in this particular channel is actually get in the nitty-gritty of things, like, get down and actually write things up and solve things up. It is boring, as the name suggests. Like science is boring in certain aspects. But it is that day in and day out of boredom which in the end gives the fruits of the labor. And trust me, that is beautiful. And the joy of creativity that you have at the end of a very long process is pretty uncomparable to other things you feel in life generally. I have been involved in science for a very long time now, and I've been thinking about, I mean, I see a lot of science videos nowadays on YouTube, a lot of science and engineering videos. Some of them have some details, some of them are not. Most of the topics are based on the entertainment values of things. But there is a way by which science is done. There's a way by which we approach a problem, we analyze it, we understand sometimes what the problem is. Sometimes it is surprising that how many times in life we don't even understand what the scientific problem we are trying to ask, what is the question we are trying to answer. And all these form a part of science. And science, as we know right now, has become a buzzword. Everybody is using the word science. Everybody throws around the word, slaps things like, oh, this is scientific, oh, this is unscientific. And science becomes a part of politics and morality and everything that surrounds us. And that is something which I personally do not find very amusing, because a lot of these aspects are based on the fact that a lot of people don't understand what science is, to be honest. Just because there are some numbers doesn't make it science. You can write a mathematical fiction. There are branches of science where some people call them as mathematical friction. I'm not going to belittle people's work, but you can write a mathematical fiction. You can put in random numbers and generate something. That doesn't mean that it's science. Mathematics by itself is a very beautiful, but it's a language. Mathematics is the language by which we express what we realize about the planet and about the world and about the universe. Mathematics is the language of science. It's a universal language of science than science itself. So that's my goal, to get into the details of things, get into different topics of physics, especially. That's because that's my area of expertise. And get into the nitty-gritty of things. Find out how the equations look like, find out how to solve the equations, understand how to frame a problem. Sometimes a big portion is the question you're trying to ask, you have to mathematize it. Just like I said, mathematics is language, but that is a very powerful language which is out there. So you have to take the problem and write it in the language of mathematics. That's called mathematizing a problem. These all are parts of how you solve a problem. You have theoretical parts of it, where to calculate something, you have experimental part of it. Sometimes you have to understand what is the experiment you're trying to do. What is the question you're trying to answer, which you need a certain experiment to be done. So all these form a part of a beautiful journey, which is science. It's a journey of knowledge. It's a journey of knowing where things are and how things stand, and understand how the world and the universe works. It's a long journey, and we are nowhere near to the end of it. But it's a journey we have been doing since the time of when we tried to explain what lightning strikes are. and we initially explained them as, God's wrath. That is actually a explanation, you can say. It's science, because people used whatever information they had and they drew a conclusion out of it. They didn't have better theory at that time. That was the theory that they had. So that is actually scientific, to be honest. There are several examples like that where we have used our existing knowledge and tried to explain a certain phenomenon. And we can talk about certain things as well, like when it comes to gravity, there are things which we do not understand. There are things even our most sophisticated theories cannot explain. And it's not because science is wrong, it's because science is always about explaining the universe, explaining the world with the amount of information that we have, and then doing experiments to find out more information about how the world works. That's what it is. So let me pull up my whiteboard and let's draw out certain things which will kind of help talk about what I'm trying to say here. Let me get my Zoom running. Okay. So the first question when you share anything on Zoom is, can you see this? And I'm sure you can see this. So if you look at it, you have different branches of science. You hear about physics, chemistry, biology, mathematics. Physics has different branches of it. So how does it all tie down? So if you draw the block of science, you have, if this is your science, it basically breaks into three pieces. Whoops. Zoom wars. Three of the major branches that we know and talk about are physics, chemistry, biology. This is what you typically learn in school. Then, of course, it breaks down and you have biochemistry. We have a million other branches of study. But typically, the relationship is something like this. They're all basically part of the same system. They're all basically part of the fact that how atoms behave with each other. And that's why you have material science and material physics, and you have biochemistry, you have biotechnology, you have biophysics. You see all these names. It's basically, the question is always like, at what scale we are talking. For example, you can be interested in studying how a single atom works or how a single nucleus works. For example, this can be the science that you're interested in. You have a nucleus, and you have electrons. And you want to know how much information can we get out of this. This may be all the science you're interested in. You can be interested in how this electron behaves with this nucleus. That is what is called atomic physics. That's actually what I worked on. You can be interested in how this particular nucleus works. That's part of nuclear physics. You can be interested in how each of this nucleus, each particle inside a nucleus works, like a proton. How does a proton work? That's part of particle physics. And high energy physics, or high energy physics and the most fundamental theories that we have. That's what they're trying to do in Large Hadron Collider, understand how each of these particles are behaving. So that's going in one scale. You're going smaller and smaller and smaller. You can go in the other direction. You can go into like doing it the reverse. You can go like, I'm not going to study how individual things work. I'm going to study how atoms interact with each other. You have one atom, you have another atom. Oh, this zoom to find a better way of sharing my screen. Promise me by the next video we'll figure this out. You have another atom interacting, and these two are playing with each other. You want to know how this interaction happens. Typically, that's where chemistry comes along, or molecular physics comes along. You can call it molecular physics, or part of chemistry. Seriously. You can be interested in knowing how many molecules form together. That's part of your material science. You can have what is called crystallography. Crystallography is the study of solid materials, solid atoms, which basically forms a part of a regular structure. And you form a crystal lattice. You might be interested in studying their behavior, and that ties into materials and stuff. So you see, it's what we call as different branches of science are basically talking about the same thing in different scales. And trust me, scales is a huge, huge problem. Going from one atom to two atom can completely change the whole thing. So there is something called a thermodynamic limit. I will talk about it later when I will talk about thermodynamics. But a thermodynamic limit is basically when you have a lot of particles. When you have a lot of particles, it is much more easier to actually do the science because you have laws of statistics taking over. That's why they say that it is very hard to predict a single person, what a single person will do, but it's very easy to know what on average a person will do. That's a statement you hear often in marketing, in data science, and different aspects of social sciences. The reason is the power of statistics, the law of large numbers. When the numbers become large, your average fluctuation, your average behavior comes up. That's where you have your thermodynamics. You have what is called thermodynamic limits. That's where you have detailed. That's actually one of the places where biology plays a role. Biology is a study of extremely large number of molecules and atoms. Take, for example, a DNA. A DNA has, I may be completely wrong on this, but I think close to a few million molecules in them, a million atoms in them, a nucleotide, and yeah, there are a lot. There can be a lot. And when you have these kind of situations where you have thermodynamics coming in, where you have laws of large numbers playing in, that's what science becomes, the methods of approach becomes very different. Biology talks about, as you know, about biological stuff like our bodies or how animals, plants, viruses, bacteria, how they interact with the world, how they behave, what their dynamics is. On the other hand, you also have something called meteorology, which is the study of weather. And while we often make fun of the fact that weather predictions are horrible, actually they have become much better. There's a huge branch of science which is going on behind it. Supercomputers running millions and billions of simulations to predict the weather, what is going to happen over the next few days. And that's again is a study of large number of molecules. The difference between, let's say, a weather science, meteorology or biology, and biology is that meteorology typically deals with a few number of types of molecules. For example, your atmosphere is comprised of primarily nitrogen, oxygen, water, and their temperature, and pressure, where your fluid dynamics also starts to play a game. Whereas biology deals with deals with many number of elements, a large combination of elements. Of course, carbon forms a huge part of our body, but you have rare elements, you have iron, you have calcium, you have multiple types of elements combining into a biological system. And that's where it plays a role. And that's what also brings a complexity to biological systems. You cannot calculate mathematically from starting from atomic structure of how a human heart beats. I mean, maybe you can do if you have like, I don't know, supercomputers of the size of the sun, maybe. I don't know. But you can perhaps do that. But at the moment, given the knowledge, and we cannot do those things. So we have to approach those sciences in a slightly different way. And that's where experiments play a huge role. A lot of those observations are experimental because you cannot derive them from what is called ab initio, starting from scratch. But one of the best examples of how experiments and theory comes together is one of my most favorite examples of how well we know our world, how precise our physical theories are. And it is one of my favorite stories. And this is going to be I would conclude today by saying this story. And it is the following. Let me wipe the board. Okay. It is how the G factor of electron. Electrons have a property called G factor. And of course, I think I understand what's going on. G factor of electron. I'm not going to go into the details what a G factor is. There's quite a bit of science involved in it. But basically, an electron, like charge, it has some other properties as well, such as mass, of course, charge and mass. Most of us know. But you also have what is called a G factor, which is related to the angular momentum of the electron and its magnetic moment, etc. So there are some other, you have spin of electrons and all these things. So there's a bit of details behind what G factor is. But basically, it's a number which we can calculate using a theory called quantum field theory. And of course, using quantum field theory, you can calculate the value of G factor. And people did that. People did calculate the value of G factor up to a place of 12 places of decimal, which means some number x dot 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Up to this place of decimal, people calculated it. Now, of course, there was calculation, and then Demelt, he's a Nobel laureate, he came forward to do this experiment. There are details to it. Of course, they're pretty sophisticated experiments, but they still did the experiment. And the story which came out of it is that when the experiment was first done, the G factor experimental was not equal to G factor theoretical. And people were pretty concerned because if G of theory does not match the G of experiment, either the experiment is wrong or the theory is wrong, or we basically have some unknown phenomena going on, which is of course exciting, but at the same time also concerning. So the person who did this theory of G factor, he went back into his calculations. And I think his first analysis took about 5 years. And again, these are hearsay from scientific communities. It's not that I actually spoke to the guy. But then he went back and redid the calculations, which I think took another 2 years, because these calculations are pretty long. Getting up to 12 places of decimal means solving or calculating a series of having about 500 terms. It's what is called Feynman diagrams and perturbation series. And when you do that, and he went back and he did actually find an error in his calculation, and he came back and redid it, and he redid his calculation. And voila, the experiment and theory matched to the 12th place of decimal. Think about it for a while. When we go to the market, we buy some groceries, we put it on the scale, we typically get it up to, like, in ounces, maybe up to 1 place of decimal right to what we want. If someone is placing stuff on a scale, the theory of the world that we have right now, that is the fundamental theory of physics, is quantum field theory. It was matched to experimental values to 12 places of decimal. That's like 1 part in a trillion. It's 1 part in a million. So that is the accuracy by which our theories work. That is the accuracy by which we know the universe, at least at one point. Of course, there are multiple other, these experiments and theories have then been developed over, and now I think it is up to maybe 13th or 14th place of decimal, or 11th place of decimal, 13th or 14th place of decimal, if I'm not wrong, and last I checked. But that's what it is, and that's what it takes, and that's how sophisticated the physics theories are. But that doesn't mean that we know everything up to that level of precision. There are a lot of information which we don't have. But this is one of my most, some days when I feel frustrated with science, I think of this story, and it makes me realize that how amazingly well we understand our world. And think of it, it is all based on human intuition. Our mind, the way we perceive the nature, allowed us to understand nature to this level of precision. So that's all for today. Thanks a lot for watching, and hope to see you again next time. Good night.